So if we pick up where we left off yesterday, we're going to look at the definition as it applies to right-hand and left-hand limits as well. So we say that f of x has a right-hand limit, L, at x naught, and we write the limit as x approaches x naught from the right, that's what the plus sign means, of f of x equals L. If for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x, x naught is less than x naught plus delta. Then, in order to have that, we have the absolute value of f of x minus L is less than epsilon. So the only difference here is that I don't have to do a plus or minus on either side. I don't have to do x naught minus delta because I'm only approaching it from the right-hand side. If we look at the left-hand limit, that's going to be opposite. The limit as x approaches x naught from the left of f of x is equal to a limit if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x, x naught minus delta, you notice it's minus delta this time because I'm coming from the left-hand side. So I'm subtracting whatever value I find instead of adding it. If I'm coming from the right, I add it to x naught. If I'm coming from the left, I subtract it. That's all this whole thing is saying. When we compared it to the two-sided limits, you had to both add and subtract it. So let's do an example of this. Here I have the limit as x approaches 0 from the right, and we can start filling in the things that we know. First, this is our x naught, is 0. It's coming from the right-hand side. There's our f of x, and there's our limit L. So we can go back to the same thing that we had been doing. Just looking here, it's x is less than x naught plus delta because it's coming from the right-hand side. So x is less than, and we have x naught down here, x naught plus delta. Then it's the absolute value of f of x, which is the square root of x, minus our limit, which is 0. And then that's got to be less than epsilon. So now the first thing that we're going to do is we can simplify what's inside. That's just the absolute value of the square root of x less than epsilon. And I can get rid of my absolute values. When I do that, normally we would have this. But remember, we're not looking at it from the minus side now because we're only coming at it from the right, so I don't have to worry about the negative. Now I can solve this by squaring both sides. This gives me x is less than epsilon squared. If I look at this piece over here now, and go back to our original definition there, we would have the absolute value of x minus x naught is less than delta. Well, if I plug my x naught in, it gives me the absolute value of x is less than delta because x naught was 0. X minus 0, this gives me x. Again, I can get rid of my absolute value signs, and that would give me x less than delta, and then negative delta, but we're coming from the right-hand side, so we don't need the delta or the negative delta anymore, because we can't subtract the delta. we have to add it to x naught. Now this is the same as this, so I know delta is equal to epsilon squared. This snow day got me working from home, and my stuff just doesn't work as good from home as it does on the computer at school. So bear with my writing and stuff. And so we have, to finish this out, we have 0, which was our x naught, is less than x, is less than epsilon squared, or delta. And that's it. Kind of the same thing we did before. We're just taking away the negative values. Now, if I was coming from the left-hand side, I would only do my minus epsilon instead of my plus epsilon, and I would only do my minus delta instead of my plus delta. All right. So let's look at our next type. If I'm looking at this one, this is sine of 1 over x. And as x is approaching 0 is what I would be looking at. You'll notice that I have this big gap here in the center. Right? And so there's nothing there. In all reality, there is something there. It's oscillating so much that our graphing tools can't even handle it. So whenever our function gets tighter and tighter in, like see how it's spread out further, and then they just keep getting closer and closer together? It means that this function oscillates too much, and it makes it impossible to find a limit. So if we're looking at as x approaches 0, then its reciprocal grows without bound. And they repeatedly cycle from -1 to 1, and it's so fast that we can't even keep track of it whenever it gets inside of here. So there's really no way for us to know that limit. And so this is one where you would just say that the limit does not exist, and because we have this big gap in our graphing tools, you would say that the left-hand limit does not exist and the right-hand limit does not exist, because there's just no way to tell. Just something to watch out for as you're approaching these problems. If you see it start to pack tighter and tighter like this and then have a gap, you know that it's just too much for our minds and the calculators to handle, and there's no way to find those limits. Limits involving sine theta over theta. So one of the facts about sine theta over theta is that in radian measures, its limit as theta approaches 0 is 1. Because if I'm coming from the left-hand side, it's going to 1. So the limit as x approaches 0 from the left of sine theta over theta equals 1. The limit as x approaches 0 from the right of sine theta over theta is just 1. My y is getting closer and closer to 1. And so since they're the same, the limit as x approaches 0 of the entire thing sine theta over theta equals 1. So I came from the left, and as I came from the left with my x's, the y's got closer and closer to 1. As I came from the right, the y's got closer and closer to 1. As x got closer and closer to 0. And so this limit of the whole thing is 1. Which is theorem 7. Theorem 7 says the limit as theta approaches 0 of sine theta over theta equals 1. And it just makes sure to tell you that theta has to be in radians. Now, I'm going to post some trig functions and trig identities on your class page, just so you can familiarize yourself with them. You'll be able to use these throughout the year. And as we start to look at more examples, you'll see why those are important. So the first one is show that the limit as h approaches 0 of cosine of h minus 1 over h equals 0. So in order to do this, first I would have to use what's called the half angle identity. And in that half angle identity, it says the cosine of h is equal to 1 minus 2 sine squared of h over 2. That's one of our half angle identities. So how does that help? Well, it makes it so that we can start to plug in. So I'm going to plug this in for the cosine of h. It gives me the limit as h approaches 0 of 1 minus 2 sine squared of h over 2 minus 1 over h. And I'm trying to show that that's equal to 0. Still don't know that it is, but we're getting there. I now have 1 minus 1. Those cancel out. I'm left with the limit as h approaches 0 of negative 2 sine squared of h over 2 over h. And I should, yeah, let me make sure I had to make that negative. So now to get rid of this 2 in the top, I'm going to divide both the top and bottom by 2. So when I do that, that's going to give me the limit as h approaches 0, and I'm dividing the top. Now because it's a negative, I can actually move that up right out in front. And then I'm dividing the top and bottom by 2. And so that's going to give me sine squared of h over 2 over h over 2. Divided the top by 2, divided the bottom by 2. Now you'll see that I have h over 2 twice, right? So if this is my theta from our last theorem, theta equals h over 2, I now have that. But I have two signs in the top because it's sine squared. So I have sine times sine. So then this is the negative limit as h approaches 0. And I'm just going to divide those out. I'm not actually dividing it, I'm just more of writing them out twice. So now I have sine of h over 2 over h over 2, which is theorem 7 because that's my theta, h over 2. So this whole thing becomes a 1. So negative limit is h approaches 0, and now it's of 1 times sine of h over 2. And now I can plug my 0 in because it won't give me a 0 in the denominator. So it's 1 times the sine of 0, which is 0. So it's 1 times 0, and the whole limit equals 0. That was fun. All right, that's where we're going to leave off today. Tomorrow we're going to do another problem like this without the half angle identity and just continue working on these right and left hand limits.